Hello, everybody. Welcome back. Today we're taking a look at a probability distribution that you may not have heard of before. So, um, let's read the problem. In an alpha particle counting experiment, the number of alpha particles is recorded each minute for 50 hours. The total number of particles is 6,000. In how many 1-minute intervals would you expect no particles? In how many 1-minute intervals would you expect exactly one particle? Repeat up to and including exactly 5 particles, and plot the Poisson distribution. They kind of spoil the fun by naming what distribution we're using here, but that's okay. Makes the problem a little easier. So for the Poisson distribution, it's a discrete distribution, meaning that it's not continuous. There are finitely, well, I mean, there are um, points that you can't subdivide at all. There's no half points or points in between points. That's a bad way of describing it, but that's you'll see in a second. So um, for Poisson distribution, the probability of some x is equal to uh, there's one parameter for this, and it's alpha to the x over x factorial e to the negative alpha. So our first order of business is to find this alpha. And this alpha is our expected value for the experiment, or mean value or average value, depending on which terminology you want to use. Um, no relation to this alpha. That's just entirely coincidence. So recorded each minute for 50 hours. Okay, this is important. 50 hours. The total number of particles is 6,000. So you can find your average number of particles per hour, but remember we want to find it in terms of minutes. So our average value, our mu of x, is 6,000 over 50 and times 60, because that gives us, so it gives us our average number per minute. So that ends up being 2, because you have 3,000 out. You have 3,000 minutes and 6,000 particles, so you have an average of 2. So that means for this experiment, the probability is equal to 2 to the x over x factorial times e to the negative 2. And then we just plug in our values for x for the probability of whatever number of particles in whatever time scale we're using, which is minutes. So in how many 1-minute intervals would you expect exactly one particle? What's the probability of 0 particles in one time unit? So that would be 2 to the 0 over 0 factorial e to the negative 2. Now, this is just equal to e to the negative 2. This is equal to 1. That's equal to 1. Trust me on that one, even if you don't believe it. So this means that the probability is approximately equal to this decimal there. What about the probability of one particle in our time unit? It's going to be 2 over, well, 1 factorial, so 1 e to the negative 2, so it's going to be twice as much. So it's going to be 2 e to the 2, or e to the negative 2, so this is going to be 0.2707. What about 2? This is actually our expected value, if you remember. It's going to be 2 squared, or 4. I'll just write 2 squared. 2 squared over 2 factorial e to the negative 2, which is going to be equal to the probability of 1, actually. So it's going to do that again. Probability of 3 particles per minute. That's going to be 2 to the 3 over 3 factorial. That's going to be 8 over 6, which is going to be equal to this decimal value. And what about 4? It's going to be equal to 2 to the 4 over 4 factorial e to the negative 2. So that is going to be equal to 16 over 24. These reduce, but it doesn't really matter. It's going to be this decimal approximation. And then finally, for the probability of 5, this is going to be 2 to the 5 over 5 factorial e to the negative 2. This is going to be equal to 32 over 120. Yes, e to the negative 2, which is going to be this decimal approximation. Now let's see, did we actually answer the question? It's always good to check over just to make sure that you're answering the question, or you're answering the question that the question actually asks. How many 1-minute intervals should you expect to know particles? We did not yet answer the question because what we found is the probability that an interval, a 1-minute interval, will have no particles, not the expected number of intervals with no particles. So what we need to do is we just need to take these probabilities and multiply them by the number of intervals that we have. So we need to multiply all of these by 3,000. So this means 406 intervals. This is going to be 812 intervals. This is also going to be 812 intervals. This is going to be 541 intervals. It's going to be 271 intervals. And this is going to be 108 intervals. So you can see that the probability is greatest close to the expected value, and it falls away further away from that, which makes sense. So these are all the numbers that we need for this problem, but it also asks us to plot the Poisson distribution. So I will show you guys this in a second. There we go. And here we go. Okay, so this is the Poisson distribution we're working with. However, remember from our previous chapters that this calculator that I'm using, Desmos, it uses it does factorials for non-integer values. So really, this should just be chopped off. This should have 1 point at every large tick mark here, and none anywhere else for this to be a true Poisson distribution. But let's take a look. So this is the probability of 0. This is the probability of 1. Probability of 2 is actually the same. Probability of 3. Probability of 4. And probability of 5. So you can see that this never quite gets to 0. There's a very, very, very slight chance that all of the particles show up in one interval, but it is extremely, extremely unlikely. You can see that it does go down pretty fast. So thank you so much for watching, and I hope to see you in the next video.